I travel a lot, and I made it a habit to do my expense reports immediately when I get back home. So the other day, I got back home from a business trip, and I logged into my banking account. But this time, it felt different. It felt different in a way that it took longer, the page took longer to load, and since I'm an engineer, I took a closer look what was going on. Firefox provides a lot of tools that allows you to investigate how many requests are made by a web page. So I opened up the web console, and I even I looked at all the requests, and I even looked at the source code. And eventually I figured out that my banking website not only loads data from the banking server, but also from a third-party script. So what is that script doing? I looked around, and eventually I realized it is one of those scripts that analyzes your mouse behavior, right? So web pages use it to actually rearrange their links to make it more user-friendly and to improve the usability of the web page. This is no good. No good because it's my private data. It's really, like when you look at it, you can see what money I spent money on whatever. So I contacted my bank and I told them, this is a problem, please, can you remove the script? And eventually I got through to the developers, and initially they didn't even realize that that might be a problem. So again, I raised my concern, please remove it. And eventually they removed it, right? So this story tells us that quite often web page authors are not even aware what they are doing. Okay. With that, I would like to welcome you all back from the lunch break, and I would like to invite you on a quick tour, on a 15-minute tour behind the scenes, starting with what is the technical problem, or how does it technically work to exfiltrate data out of the browser. We look at the current security model in the browser, and then I prepared 3 approaches that have the potential to overcome the problem of data exfiltration in the browser. But let's start from the very beginning. So explicitly, I chose a slide or data from 2012. And even back then, like 90% of web pages are powered by JavaScript, right? So that was 7 years ago, and by now I can testify that literally every single web page is powered by JavaScript, right? So it's really omnipresent. Let's take a look. So web pages load information from different origins on the web. That's how the web works, basically. And then here I illustrate the data as info.com, content.com, and also exfiltrator.com. So quite commonly, I mean, this is simplified, but when we look at it, in this case, like info.com creates the DOM, and the DOM is the representation model, the document object model that really displays data in your browser. So the info.com creates a secret, whatever that secret might be. So in my case of the banking website, it was all the different lines and all my expenses that I used on my credit card, right? So now exfiltrator.com is also loaded in the same execution context. So it's important to mention, if it's loaded in the same execution context, it has access to the full DOM, right? So on a very simplified model, what the exfiltrator script would do is, or at least in the old days, there are a variety of channels, but the easiest example is it creates a new image, and with the image it sets the source to exfiltrator.com, and then it appends whatever secret they're interested in as a payload, right? So these scripts by now are quite sophisticated, right? They take screenshots, they even record what is going on, like they have access to your full mouse movements. Okay, so now it is important to mention that the current security model that we have in a browser and that every major browser implements cannot do anything against that kind of exfiltration attacks. Let's look at them real quick. So the same origin policy itself allows objects for the same origin to access object for the same origin, but prevents objects from different origins, but only if they are not loaded in the same execution context. Like in the example I provided in the beginning, the exfiltrator script or the analysis script was loaded in the same execution context. Also, the second one here is the iframe sandbox doesn't do anything about it because we could use iframe sandbox to actually load a different document in my document, and then it's isolated from each other. But this also doesn't apply to loading a script in the same execution context. And then finally, a few years ago, we came up with the content security policy. And the content security policy allows you to whitelist where resources are loaded from on the web. Again, here, the CSP doesn't do anything to prevent that kind of data exfiltration attempts. So a lot of the problems that we are facing within content security is actually that all of the security is not binary, right? It's not full trust, it's not no trust. There is that gray area in between where I refer to it as the semi-trust, right? So moving on, how can we prevent such data exfiltration attempts? Well, I can tell you one thing. We cannot simply block all of it, right? That would be one solution. But yeah, so I prepared, as I said, like 3 approaches that have the potential to actually stop that problem or mitigate the problem. And what we have heard in the morning at the PhD lightning talks, I already saw that some people were very interested in data flow tracking and information flow tracking. So let's start with that. A quick overview. We have seen a variety of information flow tracking systems over the past years. So in a nutshell, it is like every domain registered itself in some kind of domain registry, and then we track the flow of information throughout the JavaScript engine, throughout the DOM bindings, and throughout the DOM. And then usually all of these approaches have something in common, and that is a network monitor. So before any requests are made, we inspect if the labels, we inspect the labels and potentially block the requests at that point, right? So it is important to differentiate between data flow tracking and information flow tracking. Data flow tracking only tracks the information for direct assignments, which in my opinion is very good right now because we can highlight where data actually is exfiltrated in that sense, but only as long as we don't implement it in the browser itself, because then the attackers would know, oh, they only do data flow tracking and they just do a few additional tricks. For example, branch on the secret, assign the information to a public variable which would not be labeled, and the systems are bypassable, right? So it doesn't really make sense to build it in a browser. Nevertheless, it's very important to do that in terms of research, because at the moment, since nothing like an information flow tracking or data flow tracking system is built into the browser, we can highlight such exfiltration attempts. A bunch of the drawbacks are, as I said, we have seen so many different ones, but all of them introduce a massive amount of overhead. Given the browser wars that were going on a few years ago, where we really squeezed out every millisecond that we possibly can, no browser vendor is most likely willing to build something that adds such a big amount of overhead into a browser. And the other problem, I kind of touched on that already, is that sometimes it's imprecise. So if we would only do data flow tracking, we would not label everything. And if we do information flow tracking and we run it for a long amount of time, we might run into a problem which is commonly referred to as label creep, which means that every value is labeled with the highest label in the lattice. So that leaves 2 research questions to me in that area. Can we reduce that overhead? If we can, that would be awesome, and we can reconsider building something like that into the browser. And can we improve the precision? The next one I would like to quickly touch is using blacklists or block lists, right? So we have done, and we have seen, and we're actually doing it very similarly for tracking protection. We rely on lists. And whenever, like in that case, exfiltrator.com would be loaded, and we compare the URL if it appears in the block list, and if so, we don't let the script execute at all, right? Which is fine, but the drawbacks here are it takes a long time to actually generate those lists, and there is also a long round trip time before we actually can pull those lists and load them into the browser. Like, I don't know exactly what is the time for disconnect. Dan, do you know how often we update that? Steve might know. But anyway, it takes a long time. What is interesting is or what I'm interested is, can we do better? Like, for example, could we build some heuristics in the browser that identifies if something is malicious and use some kind of crowdsource-based approach where every browser would basically report back to Mozilla or to some other third party, letting them know, oh, this one exhibits malicious behavior, and then we update the blocking list on the fly. Which leads to the next research questions for you. Can we improve the classification? And can we improve the round trip time? And then finally, I have one more approach which I personally find very interesting, and that is, can we restrict access to the DOM itself, right? So we let all of them, let all the scripts execute. Sorry, but what we could do is for exfiltrator.com in that particular case, we could allow it to access or create new nodes in the DOM, but then not necessarily access all of the other nodes or restrict access to specific nodes that we are very interested in. For example, Quan mentioned that this morning, for example, we could start by not allowing access to form elements, right? So this is quite interesting, and I see that we could do something like build some kind of wrappers, mediators around that, or even establish new attributes, and then based on those attributes, like some kind of public shaming approach, where they actually have to use those attributes, and otherwise we will block them. So as you can see, a lot of our ideas here overlap, and they are not exclusive, so maybe it is a combination of a few of those approaches. And then finally, to round all that up, it's always good if we have data, right? If we can back all of that up with data, all the decisions we make at Mozilla are based on data and on evaluating. So what I can offer is we build some of those mechanisms. We run some studies on it and evaluate if it works. We can do it to a certain percentage of our population, gather the data, and evaluate it. The data we're interested in, obviously, is quantify the malicious behavior and quantify the breakage that we are expecting around all that. So with that, I would like to summarize real quick what we looked at, and then hopefully we all agree that this is a problem worth giving attention. Hopefully I was able to convince you to actually look into some of those problems. As a summary, the threat is real. It is happening. There are a few approaches out there that could potentially prevent it. One of them is information flow tracking, using block lists, or also establishing some kind of mediators around that. I'm interested in all of the approaches, but maybe most likely there are more. This is a very high-level overview, and I'm happy to talk more in detail about every single approach. And with that, I hope we can work together and really prevent data exfiltration attempts in the browser.